guys, I am Shreya Tarse and my teammate Rasika Aute. We are here to give you more information about application of automata theory in game theory. So let's continue our topic. Here we are going to tell you about how automata theory is applied in game theory by using various automata such as infinite automata, adaptive automata and cellular automata. An abstract of this project is in game theory presenting player with strategies directly affects the performance of the player, and utilizing the power of automata is one way for presenting players with strategies. It was found that infinite automata, adaptive automata, and cellular automata are widely adopted in game theories. Thus, the application of finite automata are found to be limited to present simple strategies. So, in contrast, adaptive automatas and cellular automatas are intensively applied in complex environment where the number of interacted players such as humans or computer applications is high and therefore complex strategies are needed. So let's see detailed explanation of game theory.
So start the introduction. Basic introduction of project of automata in game theory is so any problem with interacted participants and actions can be treated as a game, and when car drivers put a plan to drive in heavy traffic, they are actually playing a driving game. When users bid on bidding based websites, they are actually playing an action game. In election, choosing the platform is a political game. The owner of a factory deciding the price of his product is an economic game. Obviously, game theory can be represented in wide range of applications. So, I have limited my examples to some 5 points where this gives a basic idea on what game theory actually is and how automata is applied in game theory. Now let's see what game theory is. Game theory is a mathematical tool that can analyze the interaction between individuals strategically. Means there are certain individuals trying to play game on team board. This game interlinks the different people in the game, and the interconnection between agents, whom may be individuals, groups, firms, are interdependent. These interdependent interactions are controlled by available strategies and their corresponding. Strategies are very important while playing the game. So if you play a card, an exact strategy can be success of the game. Game theory is nothing but a algorithm which crack the algorithm and reach to the final state. So these are the interdependent interactions.
So now let me give you more information about how automata is used in game theory. So the application of automata in game theory pays off to participants. So this means that participants are one who are going to apply automata in game theory. However, a game theory studies the rational behavior in situation involving interdependency. This quote was taken from the book called Macmillan in year 1992. This quote defines what automata is used in game theory. As game theory studies the rational behavior in situation involving interdependency, that is the basic idea of game theory which is used in automata. Therefore, game theory will only work when people play games rationally and it will not work on games with cooperational behavior. This means that cooperational behavior is nothing but where people from team inside the game where different people came across as unit and they will form a team and they will reach the success point. But game theory will not work when people will play rationally. Rationally means like if they split up in different proportion, game theory will not work. So where it will work, it generally consists of following entities. Entities are people and environment and the things which are going to develop for games. So there are this many types of entity. So let's see detailed entries. So first is player. As said in previous example, so players are the one who adopts to automata theory. So what player is? Player are where one side of game tries to maximize the gain, which is payoff, while the other side tries to minimize the opponent's score. However, this player can be humans, computer application, robots or anything. So player basically are one who used to maximize game. As player contribute to the next slide of automata, so they are here to maximize game. So whoever tries to maximize the game will reach to the success point. So next is the environment entity. This includes board position and the possible moves of the players, which is nothing but UI, user interference. As playing computer games, you will depend on the arrow and the steps in the games, which basically the thing is that which suppose the games are called arrows. Next entity is successor function. It includes action and return list of pairs, where each pair indicates a legal move and the resulting states. So screen is the function which plays where if you have to go back or front. So it will return value for your movement. For moving forward or backward, which shows the resulting states. Next entity is terminal test. It specifies when the game is over and the terminal state is reached. Utility function. It is the numerical value for terminal state. These both are correlated. So in automata there will be two values, that is 0 and 1. So 0 will be starting, which is terminal test, and 1 will be finishing, that is utility test. So if 1 is displayed, which means your game is over, that is if you have been win or you are lose. Now let's look deep in application of finite automata. Back in 1985, Neyman tries to model the fact that players can do only bounded computation. By modeling the iterated prisoner's dilemma players as finite automata. 1 year later, Rubinstein tries to show that costly computation may affect an agent utility. Rubinstein assumed that players choose a finite automata to play the game instead of choosing a strategy directly. It was clearly stated that players' utility depends on automatons' moves and the complexity of automaton structure, which is number of states of automaton. As we can assume that the players choose a finite automatons to play the game instead of choosing a strategy directly. It was clearly stated that a player's utility depends on automatons, moves and the complexity of automatons.
Recently, finite automata have been widely used to represent player strategies in game theory. For instance, the researchers of the work have conducted several experiments and the results shown that finite automata have significantly improved the performance of n players. However, finite automata are found efficient in representing simple strategies in game theory. Game theory is interested in representing simple strategies since many real time applications do not require complex strategies to achieve their goals. It means you can say finite automata make process more simpler, as people say real time applications do not require complex strategies to achieve their goal. So people can achieve their goal using finite automata, and finite automata is nothing but finite number of steps. Here is a simpler diagram which shows that R is a set of S, I and S0, where S is a set of states and I is an input symbol, S0 is an initial state and S is a transition function. In this following example, f of C10 equal to D1 and f of D22 equal to C2 and so on. The initial state is the one which an empty arrow in its direction, S0 equal to C1. So here is the structure of automata. In this diagram, C1 is the initial state and it also has self loop for 1 and 2 transition, and here is 0 transition come from C1 to D1 and 2 transition go through C1 to D1, and there is also a self loop for D1 for 0 and 1 transition, and there is a 1 transition from C1 to C2 and 0 transition from C2 to D2, and there is 1 and 2 transition for D2 to C2.
So let me explain process happening in the previous diagram. The following sequence of plays illustrate the role which infinite automata can play in representing strategies. The first player selects C as its initial state. If in this round none of the other two players played C, the total number of cooperator will be 0, which will be excluding the player itself. The transition 0 will change the current state from C1 to D1. In the following round, the agent will play D since the current state is D1. Assume that one player is cooperated, which is therefore total number of cooperator will be 1. As the people will move from D1 so as cooperator state is 1. So value will be on D1. So in next state when player will play from D again, the cooperative value will be updated to value of 2. So if updated value of 2, it will go to the D2 state. That is what explained in the previous example. So that's all information about game theory. Thank you for watching our video. Thank you.